The solenoid engine works on the principle of Beer-Savart law. The magnetic field inside the electromagnet is set up in relation with the Beer-Savart law. This magnetic field interacts with the magnetic field due to the permanent magnet to create a force, and this force is then used to drive the connecting rod.
This here we present an analysis of the force produced on the permanent magnet due to a small element of the solenoid. This force was derived using the systematically applying the Biot-Savart law to a small element on the solenoid, and the small element of the solenoid produces a small magnetic field on a small element of this permanent magnet, and this produces the force on the permanent magnet. So first we initially derived the magnetic field produced by this small element on this permanent magnet using this Biot-Savart law, and we got this two-dimensional integral and expression, and using this two-dimensional integral expression and integrating over the entire surface of the magnet, we got an expression for force applied on this permanent magnet due to the solenoid, which is this four-dimensional integration. This four-dimensional integration we solved using a Monte Carlo method, and this produced this force diagram. This force diagram shows the variation of the force as the magnet moves along this center of the solenoid. We see that initially the force is very low and it plateaus at a high point near the center of the solenoid and further decreases as the magnet moves further away from the solenoid. So once we obtained the force produced on the magnet due to the solenoid, we could use this force to calculate the turning moment produced by this force on the crank. And here we plot assuming a constant angular velocity due to this due to the flywheel. We calculated the turning torque variation as the crank rotates, and this provided the turning moment diagram from the diagram.
The setup for our design consists of a wire coil wrapped around a hollow cylinder shell, with a small guide to hold the neodymium magnets in place and at the center of the wire coil. These are attached to a connecting rod, which connects the magnets to a crankshaft. The crankshaft has a flywheel attached to it, which allows for the mechanical energy to be stored, and a cam, which every half turn hits a switch. When the switch is activated, a current is ran through the coil, producing a magnetic field which linearly forces the magnets out. This is then translated to the crankshaft, which rotates into the flywheel. This setup allows us to perpetually inputs an electrical signal and outputs a way of storing mechanical energy. The limitation of converting electrical energy into mechanical energy is the loss of energy through the mechanical parts. The biggest one that we faced whilst designing this was the friction between the cam and the switch. Whilst good contact is necessary in order to produce a consistent current to drive the magnets, there is also the possibility that the switch would create a counter torque on the cam, preventing the crankshaft from rotating. This needed to be mitigated by reducing the amount of contacts required to produce the current, as well as minimizing the amount of contact time between the cam and the switch.
Another main disadvantage of the system is the fact that we cannot use high currents or let the system run for a very long time, as the solenoid would get heated up and potentially damage the surrounding mechanical components. Taking these limitations into account, the system can be used to power anything like a small toy car or a rotational fan, basically a system which requires rotational motion.